We're live. Oh, stop. 1 sec. One sec, James. One sec, James. I have this Zoom problem again. No sound. We are live with only my sound on.
I actually used to do like live beatboxing for a band.
Oh, really?
Using for like a jazz hip hop thingy. Anyway, are we done? Nice.
Okay, audio is going through. Okay.
Okay.
We are,
But are we live now?
I need to. Yeah,
Take two.
we are live. We are live.
Take two.
Okay, hey everyone, welcome back to another Wolfram Institute Life Science stream. Please pardon the technical difficulties. Now I believe we're live and can hear us. So over the past few weeks, we've been assembling together the research that we've done so far. And what I thought we would do is give Richard the opportunity to summarize what he's been doing because he's the most he has joined the institute most recently. His project is the youngest, but he has been working quite hard on this project. And so I thought it would be a good opportunity for him to present a kind of summary of what he's done so far. It'll be a good opportunity for me since I'm writing in part a summary. I mean, we're doing it collaboratively, but I'm starting it, and so it's kind of helpful for us. And I thought that it might be interesting to a kind of a broader audience as well, because you often watch these meetings that we hold, they're focused on something specific, and we try to provide a kind of an overview. But I think it's rare for someone who is an occasional viewer to get some sense of the overall arc of the research. So I thought this might be helpful for those of you who want to understand like what is actually being done here besides just the particular agendas of specific meetings. So yeah, so Richard, please go right ahead. I don't know how long you want to take, but the floor is yours.
Yeah, we'll until till the scheduled sort of meeting ends. And
Yeah, so maybe like 45 minutes or something.
all right, yeah. So we'll do a recap of everything so far, and then a catch up of like since the last stream. Sound good?
Yeah.
Okay. So I'm just looking through my folder of notebooks to get a sense of our journey that we've taken so far. The initial project is this idea of moduli space of algorithmic constructors. We're looking at this initial state and rule pair abstracted from the sort of underlying computational formalism, which now we're looking at causal graphs. Although, yeah, and initially we are treating the finite and infinite cases slightly differently. For the finite case, we're using this concept of a minimum cost edit distance in order to provide some kind of metric between our causal graphs, or at least that's the initial sort of idea. At the limit, our causal graphs approach these objects called graphons. There are some complexities to do with dense and sparse graphons. One reference that I'm looking at actually has, you see there's a difference between, say, taking an infinite graph that's given versus a graph process where you have generations. And actually the fact that we have generations helps us a bit in this sort of metric rescaling. And so that's a point I want to make, and I want to kind of keep emphasizing. And I have this piece of literature which deals specifically with, graph processes in which you have distinct generation steps past the graph grows. And yeah, because we're firmly in that regime, I think that does make some of the concerns that we have about sparsity a little bit less severe. Okay, so there's this kind of formalization effort, which is, okay, we have this notion of cut metric, which is, given a graphon, you take this integral of the difference of your functions over all measure preserving bijections. I mean, this is just telling you some sort of distance measurement between graphons, which are themselves equivalence classes of all graphs, finite, every finite graph that they can generate. And then we started doing some actual computational experiments. So looking at, let me just find the graph construction experiments. So we will share and look at that. Share, probably screen is more convenient, so we'll do that. Okay. So this experiment was looking at, maybe I don't have the better, do I want to, yeah, we'll go to the thing, and where did we put? Probably there was a nicer screenshot. I think it was in either weekly posts. Yeah, this one. So maybe if I do this. So just to get a grasp on the idea of this, single edit operation space under isomorphism. So we're also equivalencing graphs. So at any point, if we generate a graph for which we have a previously generated graph which is isomorphic, we equivalence those. And,
hey, Richard, do you still have this? I mean, you're showing us a screenshot of it, or
yeah.
I
just still have this. I just don't want to be looking around for
that's
the
fine.
Okay. On the live stream,
Yeah, because
I do still have
it would be good to include that in the report. Yeah. Okay, we'll have to find it. Yeah. Okay.
So this, depending on the restrictions so we've got a few, is like, do we consider this single initial event to be an assumption or not? Do we apply transitive reduction? Do we always connect from past nodes into the future, or do we allow some connections from, future? Do we allow some cyclic kind of behavior in our causal graph? So for example, C is the object we get where we allow cycles. And these are interesting because they end up going up to, so at every convergence point on this C graph corresponds to a complete graph, I think. So you have the single vertex graph, a single edge. These are the V-shaped graphs, and then the triangle graph. Then, the next sort of little, whatever you want to call it, epoch is some new system of graphs, which then converge on the complete graph. And you just keep playing this game. So this is kind of an interesting structure. the previous under A, this is also interesting, and my research led me to this. In category 3, there's a particular category named poset or whatever. So if you take poset category quotiented by isomorphism, you get exactly this space, which really is our moduli space of finite graphs. In the limit, we're then looking for the space of graphons, which are equivalent, considered to be equivalent if their cut distance is less than or equal to epsilon, less than or equal to, or less than or equal to epsilon. Let's just say that. So yeah, moving away from, I want to kind of move away from the sort of formalization thing. So I'll just say as an aside, I was looking through the technical documentation just to find some statements or quotes, and I actually found a Wolfram model whose causal graph corresponds to this graph construction graph, which I think is interesting. It may be like a trivial consequence, but I think it's like, I've noticed that it probably is worth looking at why that is the case. Not just saying, oh, look, they look the same. Let's find out why that particular rule generates the same. Well, it looks like a very similar graph. It has a very similar structure. This spine down the middle and these branches, and everything looked pretty much the same. So I pasted a screenshot of that in the Discord if you haven't seen it. Anyway, this notebook is showing this process under different restrictions. Sorry, James, did you want to say something?
Yeah, I would just so viewers know, the idea here is, so there are a number of ways in which we're just kind of dipping our proverbial toe into the proverbial waters of moduli spaces. What Richard's doing here is, you're starting with, presumably just like a vertex, like a single vertex, and you're kind of applying minimum cost edits.
Mm-hmm.
And so you're kind of generating this graph of graphs where each graph will differ by its neighbor according to some minimum minimum cost distance. Yeah.
Mm-hmm. That's right. And so in order to kind of qualify as a moduli space proper, we have to have this notion of deformation, which we don't really get in the finite case. So that's why we have to go to graphons, which is kind of saying for all sort of terminating computations, they don't really live in this moduli space. They live more in this sort of constructive space, which is marked by A here. And those causal graphs are some kind of path through the space. I mean, there may be jumps if so. I actually have a notebook where I show you the given a Wolfram model signature and a bunch of causal graphs generated from each step. I show you the coverage that those systems have on these graph spaces, if you want to call them that. But for a single system, you could imagine it taking a path through this. It may not be a continuous path without jumps, though, but that's something we need to look at. But yeah, so for non-terminating computations, which, I mean, we could have all sorts of philosophical discussions about what we think the universe may or may not be. Are we living in a non-terminating computation or whatever? Yeah, that's kind of a separate issue. But if we do have non-terminating behavior, then graph limits and cut distances and so forth are the tools that we use to at least conceptualize this moduli space. That doesn't mean that we can plug in some numbers and move around the space and see the graphons. We really can't go much further than like a formal definition. There is that literature though on graph edit distance spaces, which I actually had in the notebook from yesterday. Let me see if I can open my from the donor meeting. Well, yeah, to provide more intuition for people who haven't been watching this stream, this is kind of what a moduli space of triangles would look like, or in some robotics application, this is like they call this grasp spaces, so you can kind of move around and parameterize these objects. Which
I'm wondering, by the way, Richard, that engineering example, just from the colors, I mean, is this a Mathematica thing? I'm only
Could be,
asking
yeah,
because the kind of the blue,
yeah.
purple, orange color scheme is
Well,
kind of the
those could be sort of standard palettes, but no, it's worth
they could
looking.
they
Yeah,
could be,
the
but
paper's there.
the paper's there. Yeah, right.
Yeah. So yeah, this one here is specifically talking about these orbit spaces, and these Alexandrov spaces are connected to these. But yeah, this is a piece of reference where I think we can a piece of literature which I think we can get a bit of mileage from. So essentially, they're saying that um, it's more convenient to work with orbit spaces than the in the sort of graph representation, because they're, well, anyway, they make the statement in the abstract at least that they're well investigated and easier to explore than the original graph space. So I think that maybe gives us some direction. That there's a fork in the road, and these people have shown that one of them is easier, so we should take note. Let's see. Yeah, but yeah, further with the recap, this would be an example of a graph sequence in the same way that like a sequence of rationals, or if you think about Dedekind cuts, or what was the statement I made? Oh yeah, graphons are to graphs as the reals are to the integers. That's another way of maybe thinking about it. And on screen now should provide some intuition to anybody who's wondering what a graphon actually is. So, in the limit, as we're going from left to right, we end up with these objects here, from which we can sample a finite graph of any size.
And one thing that we're trying to determine, by the way, just for viewers to understand, Richard, if you don't mind
Of course.
zooming, or scrolling up. Yeah. So, okay. So I've seen a handful of these examples of graphons, and one thing that I'm personally trying to understand is really just how many of them there are, and that we can expect to arise from causal graph behavior, because many causal graphs can limit to the empty graphon. They can also limit to the uniform graphon. And so
Yes.
this is kind of a key theoretical challenge. And we could probably start reaching out to some people who work on graphons, and people, maybe there's some people with whom
For
we can
sure.
have
No,
a discussion
I
about
was
this,
I was going to
because
mention that there's that her name is Jennifer, I think Shays. I don't know how to pronounce her surname, but she's an author on many of the, like, her name keeps coming up again and again and again, and I've watched a bunch of videos where she's giving lectures, and I think, yeah, her input also, she has a background in like statistical physics or something like that, so I think it's a very good match, and so yeah, I think if I reach out to her with a suitable prompt or whatever, and see what she says, that would be good.
yeah, I mean, the kind of the main question is, many of these graphs in the limit will tend towards the uniform graphon and the empty graphon. And then
Yeah,
I'm still trying
although
to I'm still trying to understand, like, when you wander from uniformity,
yeah,
when your matrix is not uniformly distributed, it has some concentrated distribution, has some heterogeneous distribution, like which distributions can it tend towards that are stable, and then which ones can it tend towards that fall into uh, the empty graphon?
I'm just looking for this. Where has it gone? Probably in references. I mean, this idea of a kind of growth model, because we essentially have one, that's different. If you're just handed some like large graph and you have to estimate a graph on that's a much more difficult task than if you have this generation number that you can assign to each vertex. And so there is one of these. I mean, I definitely put it in somewhere. I don't know where. If you give me a second, I can try and find it. I distinctly remember putting a thing. But where, I don't know exactly. Let's not continue the search too much.
Maybe you could just describe it.
Well,
The
I
argument.
have already previously in this live stream already, but the point is that our concerns about sparse. So you have this idea of measure rescaling that comes from that paper where they scale the domain, or they scale the, you know, codomain, whatever. Because we have this generation number on our causal graph vertices, then I think that helps us a lot in this measure rescaling. And I have a quote from the paper where they explicitly state that fact, that, you know, if you have a graph process rather than, you know, just being handed a large graph, then you can deal with the sparsity. But I'm struggling to find the. Yeah. Actually, yeah. In fact, it comes specifically from this paper. Let me just see. And actually, the researcher here is this Jennifer Chase.
Chase. Okay.
Yeah. And it's, well, they call it like birth time. And it's some statement here about how if you have this for your vertices, then you can use that as the measure rescaling. But yeah, let me look into that and actually sort of, yeah, I pointed it out in our Discord, but it's somewhere, and let's just continue with the sort of the recap.
Let's keep going. Yeah.
So in fact, yeah, I mean, for anybody who's kind of interested, this was kind of where we got to on the at least notational sort of definition of the moduli space of graphons. So you have this graphon space, you quotient by this equivalence relation, which is defined by, you know, given two graphons, do they have a cut distance less than epsilon? This is the formal definition of cut distance. And I think that's that. This was some level of the Chomsky hierarchy string rewriting system. We observed some self-similar behavior. We had some ideas about getting a quantitative measure of that. So it would be nice to look at a system and
let's just consider this one for a second. Okay, and just for people who still feel lost, part of the, if there is anyone who feels that way, I mean, I'll just say, you know, part of the goal here is to see if we can create a space that parameterizes these causal graphs, these computations. So Richard showed that nice example of the triangles, or that other example from engineering. I mean, the point is, you know, can we have some space where, you know, each point on that space is like a distinct computation with distinct kind of causal behavior? That's the idea. And in the limit, we take these graphons, which are kind of these limiting extrapolations from your adjacency matrices. So when you look at examples like this, what's interesting is, like, we know that, you know, okay, so there's this measure rescaling, which we're interested in, but, you know, nonetheless, there's this concern that many graphs will kind of collapse into an empty or a uniform graphon. We really want to know, you know, what kinds of computations have some sort of structure that is kind of with some kind of signature. I'm using that term informal. It doesn't mean anything, but just as a kind of informal way of thinking about it, has some signature that kind of holds in the limit. And so the question is, with these self-similar structures, do they hold in the limit where it's like, okay, this will be some distinct point in the moduli space?
Yeah, and I mean, all we can do down that line is to try and sort of apply this. This has a kind of, yes. So I had this idea of using Kronecker products. There is this notion of a Kronecker graph, and this tool here, the Stanford Network Analysis Platform thing, you can check out the GitHub repo. They have some Kronecker graph estimation. So you can just hand it a large graph and it will sort of estimate. I think it sort of estimates this original matrix, which is what, iteratively Kronecker product with itself to get the final graph. I'm not sure if it's, if it can return, say, multiple matrices which are composed in interesting ways, but at the end you get some kind of measure of self-similarity. And that's not, looking at, say, box counting on the adjacency matrix, which is a very naive way, which, I tried, but obviously is not good. And hence why I didn't push it any further, because it's, not a sensible thing to do. You want to look at something which is a very sort of graph-centric notion of self-similarity, not, oh, let's do some image-based, box counting thing on the adjacency matrix. So,
have you tried applying that method to this example?
No, I will. I need to build this on my desktop and run it.
Right. Okay.
Yeah,
so
and
I'll put. I want to make I'm taking notes. I'll also take notes of things that we're planning to do. So this snap thing. Yeah. Okay.
So actually, what this gives you is a matrix which is not. It's not just a binary matrix. I think it gives you some sort of probabilistic, in the same way that a graphon represents a kind of an edge probability. This Kronecker, this matrix that you get at the end, when you iteratively Kronecker product it with itself, you end up with something a bit more interesting than if it was just binary, which is what we have on screen here. So if you have real values in there, you end up with something a lot more interesting. Yeah. And
what about the manifold sprinkling?
Oh yeah. I still have that. Yeah, I still have those notebooks. So the
just
manifold
before,
sprinkling.
I know, in that notebook we were just looking at, you've done many experiments with other formal systems, but I thought maybe we could end with that. Before that, we should probably cover everything else.
Yeah, cool. I mean, they're all sort of closely related, and we're really just looking for something in which we can get sort of graphs of arbitrary size, and this has some sort of physical motivation. So, I forget who proposed the idea, but it was kind of interesting. So, we can specify these manifolds by some function. We can sprinkle vertices on that manifold, and then according to some cutoff, we can generate graphs. And so that gives us some kind of graph sequence like this. And then I applied some very sort of simple, in fact, which function was it? Let me just find fit. So I just invent some kind of form that the function will take. In this case, it's some sort of polynomial, multivariable polynomial. And we just try and fit it to estimate what the graphon would be for this sequence of graphs. And this one is just looking at a single manifold. And so it from end to end, it's like, these are the graphs that we sample from the manifold. This is what the sort of mean field of that process looks like, and here it is, and it's kind of rough because we've only sampled a certain number of times. We fit a model to that, and then we sample from that model, which basically puts us back to where we started from. So that complete journey is, kind of interesting. So from manifold to graph sequence to graphon estimation back to some graph sequence. And then we decided to make it a bit more interesting. We were like, okay, well, this manifold could be parameterized. So it's kind of like a space of manifolds. And the way I've achieved that is just by modifying the exponent of one of the variables of this function that describes the manifold, which gives me, and again, looking at the mean field of those sort of sprinkling processes gives you this. And there is some variety. It's maybe a bit difficult to see, but I can definitely see some difference between the first, second, and okay. Beyond that, it gets a bit a bit samey, but there is still some difference, certainly, between even the last two. So again, it's a function fitting business, but over more variables, not just S and T of this or whatever of this function, but also of this parameter, the configuration space of our sort of underlying system. But this is exactly the same as the previous notebook that you saw. It's that same journey of manifold to graph sequence to graph on estimation and back.
So Richard, can we, because I know you're going to get into other formal systems that you've started working with. I mean, can we estimate even crudely graphons for the causal graphs of these other formal systems? Do we have a way of doing that?
Yeah, if they're well behaved, or I mean, look what I posted the other day. This was kind of interesting. So here's like it's like symbolic regression. Oh, great! I have to do this. Whatever. So given some data points, this system here is estimating the dynamical system, the underlying dynamical system. So it's kind of like a physics-informed search problem, symbolic regression. You know, given some data, can we find a nice compact analytic form? And let's see what he says here. It's the symbolic regression method to leverage the enormous advantage offered by units in the context of physics to construct equation generation. He uses some, yeah, so it's like there's some sort of informative prior, basically, because we're dealing with physical, we're not trying to fit arbitrary functions. So it's, you know, he's able to, so this would be your search space on the left. And on the right, it's like this is some subspace of that search space if we're assuming physics. So your question, and how this relates to your question is, well, you're talking about estimating functions. It's exactly the same business, just in a different regime. So
well,
the answer would be like, how complicated is your estimation technique? How long are you willing to wait to find the answer, and so on?
I think, yeah, I mean, developing some sort of general, even rudimentary graphon estimation technique so that we can throw that technique at a number of these different formal systems. I think that can help to synthesize a lot of this work that you've been doing on Chomsky hierarchy, Fractran, etc. Because that's at least that's how I understand it, right? Which is, okay, we want to get some intuitive sense of what this moduli space will look like. In order to do that, let's not be biased by the small number of formal systems that we've actually considered. Let's consider more of them. But then we need to be able to look at their causal graphs, and we need to be able to kind of roughly estimate what their graphons look like. Then with that, so here I'm just kind of general graph estimation.
Well, actually, and just to pick up on what the importance of this, brief look at the Chomsky hierarchy is that, string rewrite systems that fall distinctly into any of those levels will only produce states which can be sort of recognized by automata of different algorithmic complexity or whatever. So, you have like bounded tape Turing machines or infinite tape Turing machines or push down automata. These in some sense sort of create this well-ordered hierarchy of computational complexities. So I think it's worth kind of, and I have done some experiments where I'm looking at grammars from each level of that hierarchy, and you can see, at least, just visually, you can see that the complexity, it does scale as you go up the hierarchy. That's not something that's kind of mentioned in any of our literature so far, and I think it's kind of worth mentioning. And the connection is, Chomsky is kind of backwards. It's like, let's look at states and try and sort of rewrite them back to some single state, the starting symbol. Whereas usually in the physics project, we're working the opposite direction. We're sort of generating. So, in computational linguistics language, they would say, like, generative grammars or or you're carrying out the productions from the start symbol in a sort of forward direction until you get to a string of only consisting of non-terminals. But again, it's just rewrite rules with restrictions on what can be on the left and right hand side and the structure that they contain. And there's things like pumping lemma and all these kinds of things which are kind of interesting in that realm. Anyway, yeah. So that's all I wanted to say about Chomsky. Did you want to say anything before we?
No, I'm just thinking we have maybe like 10 more minutes. I'm sure you want to say some things about different formal systems that you looked at. I'm just trying to remember if there's anything else key on the moduli space side that we should look at. You did create, I'm not sure if you actually showed it during this presentation, but you did also create like an embedding where you took a number of causal graphs and you estimated their distances.
I showed it, but I just skipped over it. But this was
I did have a question about this, which is I found in your notebook a space that's quite similar to this, but doesn't have the callouts. And I was wondering.
Oh, these were generated offline because I'm not well versed enough yet with Mathematica graphics functionality to do this myself. So I just did it by hand.
Okay, you did by hand. Yeah. We can make some real callouts for these. That shouldn't be hard.
These are the actual graphs, but it was just, we want something for the weekly update, so let's just get it done kind of thing. But what we're seeing here is, a particular Wolfram model signature. I've evaluated all those systems up to some number of steps, generated the causal graph. I'm looking at the pairwise edit distances between these things. And then I use this multi-dimensional scaling to splat them into Euclidean space. And that's really more just as a kind of educational thing, maybe, or like just to explain what's going on more than anything else, to give an intuition behind what a space of computations might even mean. So and it does raise some sort of interesting, like maybe you would call it not philosophical, but interesting sort of, what would it mean for, because each of these points, as you go to some sort of infinite limit of causal graphs, each of these things without the embedding would be some kind of infinite dimensional vector. And so this is the distance matrix that I get. But, if we're talking about all computations and all causal graphs generated from all computations from every conceivable computational system that you can imagine, up to the principle of computational equivalence or whatever, then each row in this matrix does become some unique point, but becomes infinite in extent, or infinite in dimensions. So, and I don't really know what more to say about it than that, because it's
no, it just it's just it's an kind of an introductory gesture to help people kind of understand.
Because the embedding doesn't really have much. It's not like we're saying, oh, we're going to put all computations on the 2D plane, because you can't. You sort of
in the limit we're dealing with graphons anyway, so it becomes quite different.
Well, it becomes different, and it becomes easier, but our space of computations shouldn't contain only non-terminating computations. So if it also contains terminating computations, then they live. That's why before I mentioned this idea of a boundary and an interior, the interior containing all finite causal graphs, and the boundary of this thing containing all graphons. In the same idea as this Escher painting, which has this Coxeter projection idea, where the further you travel towards the boundary of the circle, the shorter your spacings become, until they become infinitesimally small. Anyway, so that's that. yeah, if we're ready to move on, the last thing is more just trying to explore sort of infinite graphs, non-terminating computations, and
But
also
actually,
to yeah,
I'm
you do have
curious
more.
with the thing you just said though.
Mm-hmm.
I mean, yeah, this is we discussed this before, but I hadn't thought about it for a little while. So
Mm-hmm.
this idea so in the moduli space, you could also include finite computation. I mean, hmm.
Yeah, because we don't want to restrict
So
ourselves to.
how would you, maybe this is simple, but I can't tell at the moment. How would you, what would be
Well,
the
the problem,
distance between, what would be the distance between some graphon and,
and yeah,
um,
exactly.
yeah,
Yeah, you're yeah. Well, I mean, essentially, it's kind of uncountably infinite. The distance between a graphon on the boundary and some finite computation on the interior. And also, what's um tricky is that we've got kind of both of these. So this is a slide from a talk. I have the link in the Discord, but this idea of like continuous and discrete moduli spaces. I don't really know if it makes sense to sort of mix them, and we can deal with them sort of separately, but and one of the challenges behind doing any kind of computational experiments is also the undecidability. Like, sure, we can make some inductive proof that shows that a particular system is never going to terminate, for example, but in the general case we can't. So we have to, we can't just enumerate a bunch of, say, string rewriting rules and select those that are non-terminating.
so you mean, for instance, okay, so we have some computation and we estimate a graphon for it, but we don't actually know,
Yeah.
right?
Yeah.
Except for certain cases where it's been proven.
Yeah, and most people can look and say, oh, for sure that we can, but I'm just saying there's no general, there's no way that we can write some function. It's just the halting problem. There's no way that, or it's the non-termination dual of the halting problem. For example, in term rewriting, there are techniques for doing termination proofs and so forth, but they take, you take your rule set, you translate it into some sort of SAT problem. But of course, any SAT problem can come back with, like, yeah, unsatisfiable, or no solution even.
So I'm just thinking through things to do. So I think a general graphon estimation, just so that we can get some sense of what the limiting behavior is for some of these causal graphs. I think getting causal graph production, so like, when you're working with these new
Well,
formal systems, like
actually,
say,
I think the Kronecker estimation thing kind of gives us something a little, at least for the self-similar looking systems, which one of those Chomsky things looked like. That gives us, it's kind of analogous to a graphon, but it's not in the form of a graphon. It's a model from which we can sample an arbitrary large graph in the same way that we can do with a graphon, but it's not in the form of a graphon. It's in the form of some real valued matrix which you iteratively sort of Kronecker product with itself or whatever any number of times. Do you get what I mean? So it's like the Kronecker estimation is sort of one alternative to graphon estimation, but it's like a different means to the same end.
okay, I'll put
Yeah.
that down.
Yeah.
Can you even sample from it if it's infinite power?
Oh, no. You just do it to some finite number. So you give this tool, this cron fit tool, some finite graph that you have. The idea being that then once you get the Kronecker parameter matrix, now you can keep applying it and generate larger graphs or smaller graphs with the same self-similarity sort of properties. That, do you see what I mean? And what I'm hoping is that this Kronecker parameter matrix, we can kind of reduce down to some single scalar sort of metric. Something which tells you, oh, this graph is very uniform, or this graph has, scale symmetry. And yeah, it's just, because first I tried some box counting thing, but for a start, this is not a sort of well-behaved, it doesn't show this over the whole, yeah, maybe if we permute these vertices, we could get something that looks nice. Probably we could, but, think about how long that's going to take. So do you see what I mean? Like rather than using like box counting as a fractal measure, I want to explore this confit idea. But yeah, of course,
right. So
yeah, I mean,
Snap.
But next question is kind of interesting though. Can you from a finite matrix, which we sort of iteratively Kronecker product with itself to some infinite number of times, can we actually get the graphon from that? That would be the question. So the tool would spit out something like this, or I don't know, 3x3. It has real values in it. Now, is there some way in which you can resolve some function on the 0-1 squared domain from that? I think that's the question.
Actually, I still don't quite understand. So is the idea this matrix that you're highlighting is the point is the point that is what we begin with, and then we would Kronecker product in order to
get this.
Isn't it kind of cheating? Not to be rude or anything. It's like we have some matrix that seems to have some self similarities, and then what the idea is that we would use this Kronecker product in order to get something that really does have self similarity. But what the point? I guess the question is, I shouldn't say it's cheating, but I guess the point is, what does it have to do with the underlying computation?
It's trying to coarse grain. It's trying to coarse grain the graph into some more compact representation, some estimation, some like little subgraph that can be used to generate the large graph that we hand the tool. That's the idea. So we run something for, some large number of steps or whatever. We observe some similar behavior that we don't really understand yet what that kind of means in causal graph land. I mean, we could think about that, but look, here it is. This is the system here. Resource function, whatever, S goes to whatever.
Mm-hmm.
I took this from a particular example. I think it's a context sensitive gram. No, anyway, whatever. It's one of the levels of the Chomsky hierarchy. It gives us this. So the causal graph has some kind of self-similar connections, and as you keep increasing the number of steps, it doesn't go away. It sticks around. So so presumably there is some more compact representation of that from which we can generate at least even an approximation of what we see there. And here is just a sort of example. Yeah, it's contrived, sure. Like I've got this, I do the Kronecker product, I get this. Yeah, it's contrived. But using these estimation tools, we would get something that's a bit less kind of perfect looking than this. And from what I read, you're not getting like these binary matrices. You get some sort of probability, like a connection probability, which is fine because that makes sense in the graphon regime. And then the next question is like, if you were to iteratively Kronecker product some matrix with itself, can you find the function for it? Presumably you can. Maybe. I mean, there are some kind of spectral identities that relate to Kronecker product and so forth that I can't remember offhand, but there are some statements about the way that eigenvalues behave between different iterations of a Kronecker product and stuff, which is interesting because especially if we're starting to do this spectral treatment of things, although that's more on hypergraphs, but we should still build up intuitions for graphs. Is that okay, or do we want to talk about this some more?
No, that's okay. Yeah. Okay, so so considering Snap and Kronecker either as alternatives or as kind of complements to this graphon treatment, Also,
Okay,
kind of, yeah, kind of getting general graphon estimation, even crude, as you're working with these new formal systems. Also, being able to get causal graphs. So I think I saw like a causal graph for some of the Chomsky stuff because it's just string rewriting, so that's helpful. Understanding and employing some of these measure rescaling techniques. I think better understanding, even intuitively, the moduli space of graphons itself. Because like,
how it
okay,
fits with the finite case, yeah.
yeah, okay, yeah, hold on, I'll write that down too.
Yeah, like how do they live together within the same object?
Well, the other question is, even if as an initial step, if we were able to understand, say, the moduli space of graphons, because it's not necessarily the case that all causal graphs that will obtain, like if you take the graphons for all of those causal graphs, it's not necessarily the case that that will be all graphons. That's actually something for us to just figure out as well. But even if we have some intuition about moduli space of graphons itself, and this seems like something where, like, at some point we do so much research kind of internally, but I feel like if we go out to the community and we start asking people, we're trying to gain some intuitive grasp of what the moduli space of graphons might look like, people could probably chat with us. We could probably try and determine that. So understanding really what the moduli space of graphons overall looks like, and then also trying to get some intuition, how many of these graphons, which of these graphons will we actually encounter, and do we have some technique of kind of determining, which kind of graphons can we discard, and then if we know which ones we can kind of discard,
well, if any, because we've made the sort of conjecture that perhaps you can just generate arbitrary causal graphs, that you can sort of cheat and set up some set of rules that's going to give you any graph that you like, but well, as under the restrictions that we have, initial event, transitive reduction, whatever we want, whatever restrictions we want to apply that tell us what these causal graphs must sort of obey. But
yeah,
given
given
that we should be able to generate sort of arbitrary graph, because for any state that we know we will reach, you can sort of write some rule where that state happens to be on the left-hand side, and now you can set the right-hand side up to be whatever you like in order to continue the graph on as you like. So
I think a conservative thing you could do is like, okay, let's say we have some idea of what the moduli space of graphons looks like. Then you ask, okay, if we just take graphons for transitively reduced DAGs, then how many of these which of these graphons do we throw away? And if we can get some understanding, yeah, if any, and if it's none, then just understanding the moduli space of graphons will be sufficient. If there are some kinds of graphons that we know we can throw away, conservative, then we can say, okay, we can discard this many graphons. Now we can consider this moduli space. This is, I mean,
yeah,
it's
no, you're right.
It's still unclear. It's unclear exactly to what degree of specificity we can speak of the moduli space of these causal graphs. But I think, we're doing all this kind of, I don't want to call it, it's kind of inductive approaches where we're looking at specific computations. And I'd like to, approaching this problem from this inductive side as much as possible for intuition building is helpful. But I think that ultimately, if we want to actually speak to the moduli space itself, we'll probably have to do it from the opposite side, which is start with the moduli space of all graphons, which people who work on graphons or algebraic geometry might be able to help us with, and then understanding conservatively, are there some of these that we can discard? And then that's,
there's no literature whatsoever on graphons for graphs which are generated from computational processes. It's all about social networks, LinkedIn, Facebook, whatever. It's all about like real world or some kind of graph models like the Erdos-Renyi graph model, or there's a whole family of these growth models that they use and study within that literature. But there's absolutely none on sort of like infinite limits of computational graphs or graphs generated from computational processes. And so yeah, it's kind of a new field of study.
Yeah,
So I think, to be
it's
honest,
funny. This, yeah.
we'll be putting more challenges to them than anything else. But yeah, it will be interesting to get some feedback and maybe some pointers.
I mean, it's kind of funny because this is happening in Carlos's project too,
Mhm.
right? Where trying to answer some of these basic questions motivated by computational interest ultimately like encounter some new questions that people that we haven't seen people consider. Um, well, oh wow, it's already the top of the
Yeah,
hour.
yeah.
We didn't get to some of the
That's
work
okay.
you've done on new formal
We can
systems,
do it
but
next time. Yeah.
we can do it. Yeah, we can do it next time. Okay, well, this was kind of a loose
Recap.
presentation
Mm.
of what Richard has been doing and some kind of discussion on kind of obvious kind of next steps to take. I mean, I should point out like Łukasz, Carlos, Nick, they've been here for much longer. Richard has his output has been sizable, but he hasn't actually been at the Institute for that long. So I've been kind of happy to see him come up with ideas and explore many different facets of this. And I think that we've been able to kind of extract from this series of exercises some promising things to consider. And so I think what we'll probably do in the report is kind of present a narrative of everything that Richard has done, and then present kind of concretely the next steps that we want to take. And I think that these next steps, when put together, because it's like on the theory side, on the computation side, it's on the it's on I don't know what to call the kind of the graph. It's like on the kind of on the estimation side. Um,
Mm.
all of these put together, we're still not sure if these different methods will actually meet. You know, we have this kind of problem that's like on the one hand, you have this kind of limiting object. To what degree can we speak about it? On the other hand, you have things like generating graphs using minimal cost edits, which is like a very inductive low level approach. We have some kind of estimation techniques that we can develop, which are kind of meso, and it's not sure how confident we'll be in them. And so I think kind of my personal goal, I'm interested in Richard's perspective on this, is basically just to see like, you know, how well can we do on on uh, with what degree of resolution can we speak to this limiting object? How much can we show the viewer that's intuitive on the low level side? And how well can we how well can we estimate things kind of in the meso side? And there still might be these kind of gaps between them, but I mean, hey, this is a project about kind of, you know, it's like parameterizing computations in general, and it's
Yeah,
using
yeah.
like infinite computations. So like obviously
Mhm.
connecting going from the low level to the high level would just, you know, it won't ever happen in full. And so we're trying to just give these kind of snapshots of the low, the high, et cetera, to give people some understanding
Yeah,
of this concept.
you're absolutely right. I mean, the minimum cost edit distance, that problem is a search problem that's NP hard, I think. So, which is exactly why I tried to come at it from the other end, which is let's just construct arbitrary graphs of unit cost, because then I don't have to take sort of like computational causal graphs and calculate their actual distance. I can just build up arbitrary graphs, you know, assuming that we will span that space of all possible transitively reduced DAGs. That seemed like a kind of reasonable way to go. Sort of, yeah, that sort of is like more constructive. The other way is sort of more computational.
Yeah. I mean, it's like raw computation, kind of constructivist approach, and then at some point there's kind of the almost just kind of pure math
Mhm.
approach, and then there's like the kind of engineering tricks estimation approach in the middle. So I think it'll make good use of Richard's kind of talents in these various areas. So anyway, so to viewers, I hope that was helpful. It was a bit kind of loose, and you got to look at our Discord page and things, but hopefully you got some understanding of what's been done. And if you want to understand more, we will be releasing a report describing all of each of these projects in some detail, and so we'll keep you apprised of the release of that. So well, thank you, Richard. Thank you, Nick. Nick is sitting somewhat farther from the camera, so we know that he wants to go. That's Nick's sign of when he wants to go. So anyway, thank you all, and we'll see you next week. Cheers.